So, hello to everyone watching on YouTube. So, since no one has joined the session in person yet, so I'll be waiting for like let's say 5 6 minutes before discussing the problem so that a few people can join the session in person also. So yeah, I'll be starting in 5 6 minutes for everyone who's watching on YouTube. Okay, so hi Rasika. I guess we can start. So so if anyone else joins, maybe they can ask any doubts if they have till then. So I guess we can start. So first of all, just to reintroduce myself, so I'm Lakshay Saggi, the problem solving TA for the Tuesday sessions for the NPTEL course of Introduction to Competitive Programming. So this will be, I believe, our sixth session, and in this session we'll be talking about shortest paths based algorithms like Bellman-Ford and Dijkstra's and stuff like that. So yeah, once again, I'd be assuming that you have seen the lecture videos for this week, and we'll be solving problems related to that. And like, if you have any doubts or anything, feel free to ask me about it in chat, and yeah, I'll try to solve it to the best of my capabilities. Also, if there are any issues that you're not able to see the screen, or there are any audio issues, please inform about that also in the chat. So yeah, I guess we can get started then. Maybe I will just share my screen and we can get started with solving the problems. So let me just share my screen first. So I hope my screen is visible. If it is not, please inform me via chat. Otherwise, I'll just assume that it's visible. So yeah. So I guess we can just get started with the questions. So today's problems will be mostly on shortest paths and algorithms related to shortest paths. So yeah, I guess we can get started. So the first problem is consider the following strategy to solve the single source shortest path problem with positive integer edge weights from a source vertex S. So the problem is to find the shortest paths from a single source, and we are given positive integer edge weights. So every edge has a positive integral weight, and we have a fixed source vertex S. So the algorithm or the strategy which the problem suggests is just to replace each edge in the graph with of weight W maybe. So replace each edge in the graph with weight W by W edges of weight 1. So what it means is, suppose an edge has a weight W, then just replace that edge W by W consecutive edges of weight 1. And these should be connected by new W minus 1 intermediate nodes. So for example, you can see here that initially suppose U and V had an edge between them of, let's say, weight 3. Then what we do is we insert, like, let's say, two new nodes N1 and N2, such that U and N1 have an edge of weight 1 between them, N1 and N2 have a weight of 1 between them, N2 and V have a weight of 1 between them. So we can split this edge of weight 3 into three edges individually of weight 1. And now the problem suggests that just run BFS on the modified graph to find the shortest path to each of the original vertices. So now the problem suggests, okay, now that okay, now the problem suggests basically that we have converted the weighted setting of the graph initially. Initially, all edges had different weights. Some edge may had a weight of 7, some may have a weight of 3, some may have a weight of 10. But now we have reduced this to a problem in which all edges have weight 1 only. So it's similar to the unweighted setting. And now the problem says, as we know, in unweighted setting, to find the shortest paths, we just need to run the BFS. Now the problem says just convert this into unweighted setting where all edges have weight 1. And in this problem, now just run a BFS on the modified graph to find the shortest path. So now the there are four options. So first of all, like, this is a strategy suggested in the question. First of all, we don't even know if this strategy is correct, right? So the problem asks this only, that is this strategy will not solve the problem correctly. This strategy will only work if the graph is acyclic. This strategy will solve the problem correctly and is as efficient as Dijkstra's, or this strategy will solve correctly but is not efficient. So first of all, just always keep in mind that whenever we are solving the problem, before looking at efficiency of an algorithm or any strategy, we first need to ensure that what we are doing is actually correct, right? So first of all, we should decide whether this algorithm will be correct or incorrect. And after that only we should decide whether it will be efficient as Dijkstra's or not efficient as Dijkstra's. If this is incorrect, then there is no use in comparing efficiency, since an efficient algorithm which is incorrect is of no use to us. We only want correct as well as efficient algorithm. So what do you guys think? Will this problem be, is this strategy correct? Okay, so Rasika has typed in the chat that the answer should be D, and this that which is this strategy will solve the problem correctly, but is not efficient as Dijkstra's algorithm. So yes, Rasika. So actually your answer is correct. So the correct answer is here actually D, that the strategy will solve the problem correctly, but will not be as efficient as Dijkstra's algorithm. So, and why is this the case? Maybe I'll just tell you guys why is this the case. So first I will write down the answer. So the correct answer is option D is correct. And why is this correct? So it can be easily seen that we are converting every edge into multiple edges, right? So an edge of weight 3 will be converted to 3 edges of weight 1. An edge of weight 7 will be converted to 7 consecutive edges of weight 1, and so on. So it's sort of easy to see that the distance between u and v does not change. Like here, distance initially in the initial graph, distance between u and v was 3, and in the updated graph also, the modified graph also, the distance between u and v is 3. Even though there are more edges, but all edges have weight lesser, so the distance still remains 3. So that's why. So that is why the algorithm is actually correct, because it preserves the shortest paths actually. So it's not too difficult to see that the not too difficult to see that the algorithm is correct. So first of all, we are arguing about correctness, and only after that we'll talk about the efficiency. So it is not too difficult to see that the algorithm is correct. And why is this the case? This is because the algorithm preserves the this is because the modified graph preserves the distances between the pair of nodes. Pairs of nodes. So actually this part is quite trivial that the algorithm will be correct, but now we have to compare its efficiency. Like, is this efficient or is this not as efficient as Dijkstra's? So one thing to look at here is actually uh, in how much time does the BFS on a graph run? So what we are doing is we are converting the original instance of the graph into an updated graph and running BFS on it, right? So let the original graph have m edges. So let's call the original graph as G and let it have m edges and n vertices. Now what will happen is the modified graph G prime. So let's call the modified graph G prime will have, so this modified graph will have some more edges, let's say m prime edges, and some more vertices, let's say n prime. Total vertices is n prime. So what happens is our algorithm, so the given strategy runs in, so this will run in order m plus n time, but this time will be linear in m prime and n prime, because we are these will because we'll be running BFS on G prime, and G prime has m prime edges and n prime vertices. So the given strategy will run in order m prime plus n prime time. I hope this is clear to everyone. This is just the time complexity of BFS. But uh, in how much time will Dijkstra run? But Dijkstra runs in time. So in how much time does Dijkstra algorithm run, guys? Would anyone like to answer in chat? So we'll be running Dijkstra on the original graph directly. So it has m edges and n vertices. So yeah, so Rasika has answered that Dijkstra runs in order m plus n log n time. So yeah, good job, Rasika. So Dijkstra will actually run in order m plus n log n time, right? So on first look, you may think that, oh, order m prime plus n prime does not have this logarithmic factor, so maybe this is smaller. But note that actually m prime can be much larger than this m here. So uh, so actually this order m prime plus n prime can be much larger than this order m plus n. And why is this the case? So maybe I should just first mention. So the modified strategy. So our strategy may take more time than Dijkstra, as M prime can be much larger than M. And why is this the case? So just it can be seen easily because actually uh, there are multiple edges for a given edge in the, so suppose there was only, so it can be seen in this example also that the original graph had only one edge of weight 3, whereas the updated graph has a three edges of weight 1 now. So let's assume just that instead of this weight 3, this edge had a weight of, let's say, 1 million. So Dijkstra will still run in order m plus n log n time, whereas our algorithm will now run in something like an order of million time, because now we'll have to introduce 1 million edges here in the graph. And as we introduce 1 million edges between u and v in the modified graph, so the VFS on it will take something like a order of 1 million time. So which is obviously much larger than just running Dijkstra directly on these two domains. So I hope everyone understands why is this the case that M prime can be much larger than M. Because as you can see here, so there was this example of weight 3, but suppose this weight 3 was instead of weight of million, then it can be seen that we'll have to insert million edges here, and then M prime will be million, whereas M was just equal to 1. So and now this million can also be made arbitrarily large, and it can be further increased. So yeah. So that's why this is not as efficient as Dijkstra's algorithm. So I hope everyone understands this. If there is still any doubts or anything, you can ask me in chat and I'll try to answer. Otherwise, I'll be moving on to the next question. So coming to the next question, then maybe I should move on to the next page. So the second question is, so we are given this graph which contains this many nodes, and all these edges have some weights also. The weights for all the edges is also given. And now the problem is asking us to just apply Dijkstra's algorithm from the vertex A on this graph. And now we need to answer uh, certain statements related to Dijkstra's algorithm. So there are some options given to us. So we'll need to first apply Dijkstra's algorithm on this graph, and then we'll need to answer these. So, so let's just start with running Dijkstra's on this problem. So I hope everyone understands how to run Dijkstra's algorithm. So we sort in Dijkstra's algorithm we sort of first maintain a distance array from the source to all the vertices, right? So maybe I should insert a table here so that let me just insert a table here, guys. So this table will actually ABC A G G H. Right. So now this table will be storing just the distances. Uh, so this table will be storing the distances from A to all the other vertices, which are B, C, D, E, F, and G and H. As we run along in the as we move along in the algorithm, these distances will get updated as is done in Dijkstra. So I'm just trying to simulate Dijkstra's algorithm for you guys here using this table. So maybe I should shift the table upward so that it is along with the diagram. Right. Okay. So what happens initially is, so initially we haven't visited any edge. So we'll be thinking that all the vertices from B to H are at an infinite distance initially, and A is at a zero distance. And now what happens is we look to the closest uh, we look to the closest vertex now. Uh, or maybe we just look at the vertex which is at the closest distance right now, which we call relaxing an edge, as was done in the lectures. So you can actually see that so the closest vertex to this A is this B vertex right now, and the edge connecting A to B has a weight of 1. So the distance of B will now get updated to 1. So this maybe I should just copy all these values and just update the distance of B to 1. And why is this distance of B updated to 1? Because as we started out from A, B was the nearest vertex to A, which was the distance of 1. So that's why B's distance gets updated to 1. And now what happens is, now we have visited both A and B, and now we look to see which vertex is now nearest to these. So maybe what can be seen here is that, so the vertex D here, so it can be seen that actually the vertex D here has a distance of 2 from A, and from this vertex B was already at a distance of 1, and now this D is at a distance of 3 from B. So this vertex D has a distance of 4 from this A, from this path, whereas it has a distance of 2 from the initial A to D path. So for D, the nearest, so for the vertex D, actually the nearest path is of distance 2. But maybe there are other vertices which are nearer to, so maybe there are other vertices which are nearer than this D, let's say, to the A and B set. So, but you can actually see that the vertex B, from vertex B, actually E and G are distances of 5 and 6, which is obviously more than 2. Similarly, from vertex A, this vertex C is a distance of 3, which is again more than 2. So actually this vertex D will be the nearest vertex. So at next point of time, we'll update the distance of D, and its distance will actually be equal to 2. So I'll just copy this. And now D's distance is set to 2. So by the third time our algorithm runs, so we have found out the distances of B and D from the, yeah, from all the vertices. So from the source. So now in the next path, now we'll again look to find out for the remaining vertices. The remaining vertices are the C, H, E, F, and G. So out of these, which of these is the closest to the existing vertices? So now it can be seen that the distance of h will be at a distance of something like a 4 from D, right? So we have visited these A, B, and D. So now h will be at a distance of 4 from this D, and D was already at a distance of 2. So h will be at a distance of 6. But maybe 6 is not the minimum. Maybe the other vertices are at a nearer distance than this. So now we'll try to see if they're So now we'll try to see for all these other vertices if any of these C, E, F, and G is nearer than 6, is near to distance nearer than 6. And it can be actually seen that this vertex C here is actually at a distance of 3 from A, and A was initially at a distance of 0 from itself. So this vertex C is actually at a distance of 3 from A. So we know that C is closer than H at least. And it can actually be seen that so you can also see that this edge, this vertex E, F, and G will also be further away than C, actually. So because this vertex E has a distance of 2 from D, and D is already at a distance of 2, so this E is at a distance of 4. So that's why E is further away than C, which has a distance of 3. And like it can be seen for all the vertices that C will come out to be the closest. So the distance of C will get updated to 3 next in the next row, or in the next run, in the next iteration. So note that the values which I am fixing, so note that the values which I'm fixing are actually the distances which we have already found out. And these inf distances are something which we still have to find out. These distances are fixed that we know that B will be at a distance of 1, C will be at a distance of 3, and D will be at a distance of 2. So after visiting these A, B, C, and D, and now we'll move on to find out the distances of these H, E, F, and G also. So now actually it can be seen that H will be at a distance, H is at a distance of 4 from D. So let's find out the minimum distance of H. So H is at a distance of 4 from D, and D was already a distance of 2. So if we take the path from D, H will be at a distance of 6. So, and there are out of A, B, C, and D, H can only be visited via D. So H will have a minimum distance of 6 right now. But maybe these three, E, F, or G, may have a lower distance. So let's see for the distance of E. So as can be seen, E has edges to C. E has an edge to C. So through C, E has an edge of weight of 7, and C was initially at a distance of 3. So this path, so coming to E via C will be a path of length 10. But maybe E can have other paths which are smaller. So we can see that if we take the path from B to E edge has a weight of 5, whereas B itself was a distance of 1 away. So that's why 1 plus 5 will give 6. So E will have a path of length 6 via B. But we also have this vertex D. So maybe this D will be give us a shorter path. So note that B, A, B, C, and D all have been visited till now. So we can only use these 4 vertices while determining the distances. So now D has an edge to E, and this edge is of length 2, and D was initially at a distance of 2. So going to E via the edge from D will give me E at a distance of 4. So from this, we actually know that E will be at a distance of 4. And we had realized that H was at a distance of 6. So actually, we realized that E is actually nearer. So maybe we'll have to visit E. Let's see the distances for F and G also first. So we know for now the closest vertex is E with a distance of 4. But we have not checked these F and G here till now. So now let's check the distance for this F. So for this F, actually it can be seen that F only has an edge out of these visited vertices of A, B, C, and D to the vertex C. And this edge has a length of 4. and C was already a distance 3. So 4 plus 3 will give a distance of 7 for the vertex F, which is greater than the distance 4 for this vertex E. So maybe so E is nearer to than F also, but maybe G is nearer to than E. Let's see for G also. So for G, it can be seen that it only has an edge to B out of the 4 visited vertices till now, and this edge has a length of 6. So this itself is greater than 4. So G will be definitely further away than E. So actually, we arrive at the conclusion that E is the nearest one. So E is actually the nearest vertex. So what this and it has a distance of 6 as we had already found out, or it had a distance of 4 because it had an edge of length 2 to D and D was already a distance of 2. So E has a length of 4 now. So maybe we'll just copy these values and update the distance of E to 4. And now what happens is these F, G, and H remain, and now we'll need to find out for these F, G, and H as well. So maybe we can find out for F first, or maybe we can find out the distance for H first. So the distance to H. So now note that we have visited the vertices A, B, C, D, and E. So we can consider all the neighbors of H, which are amongst the set A, B, C, D, and E. So H has an edge to E here, and E was at a distance of 1. E was at a distance of 4. So if H takes the path via E, then it will have a distance of 1 plus 4, which will be equal to 5. Whereas if H takes a path via D, it will have a distance of D has a distance of 2, and H and D edge has length 4. So H will have a distance of 6 from this side. So actually you can see that this H to E will be, so while doing this iteration, you will see that this H to E will actually be the closest path H can take, and this path will be off. So this will result in a path of length 5. And similarly, you will also realize that F and G will be further away. So while doing the same arguments which I did till now, you'll realize that F and G will be further away than H. So H will be the minimum distance vertex here, and it will have a distance of 5 from the source. So yeah, so in this iteration actually, so I've not done everything for this iteration because we are doing similar things, and I've just said that this iteration, you'll realize that H will have a distance of 5. And similarly, in the next iteration, what happens is, so first of all, like I hope everyone is able to follow. If you're not able to follow, feel free to uh, let me know via chat and I'll try to explain it again in better words. So yeah, otherwise I'll just assume that everyone is understanding what's going on. So now in the next iteration, now we need to still find out the distances for F and G. So now we know that F only has among the already visited neighbors an H to C only because G is already G is not visited yet. So F only has a visited neighbor of C, and it has a length of 4. So what this means is, and C was already at a distance of 3. So F will have a distance of 7 if it goes via C. So the minimum distance for F in this iteration is 7, whereas for G, the minimum distance will be, so G has an edge to E. E is at a distance of 4 and G to E edge of length 2. So G will have a path of length 6 via E. And this will be actually smaller than the 7 length path which F had. So that's why actually G will be the next vertex whose distance we'll fix. And its distance will be equal to 6, as distance from A to E was 4 and then E to E, G is 2. So we just change the distance of G to 6 now. And now comes the last vertex f, and we need to fix its distance. So this f has a distance of 2 from G. So G already was a distance of 6. So now via this G to F edge, F will have a distance of 8, 6 plus 2, 8. Whereas if it takes the path from C to F, C had a distance of 3 and C to F has a length of 4. So this path will take 3 plus 4, which is 7. And 7 is less than the 8 length path here. So actually F will be at a distance of 7 here via taking the path through C. So I hope everyone was able to follow that. Here we'll be fixing the distance and the distance of F will be 7 here. And maybe I should bold out the values which we are changing in every iteration. So this is the value which we fix in this iteration. This is the value which we fix in this iteration. C distance is the distance which we fix in this iteration. Then E distance is fixed here. Then H's distance is fixed here. Then G, and lastly F. So yeah. So the final shortest distances which we obtain are something like these. Okay. Okay, so Jay is saying that he did not understand H with value 5. Okay. So Jay did not understand this step. Okay, Jay. So I'm assuming that you have understood everything till this step. Okay, so till this step, what we have done is we have visited the vertices. We have fixed the distances for vertices A, B, C, D, and E. So we have fixed for all these, and we need to fix out the distance for one of these F, G, and H now. So in every iteration, only one vertex distance of one vertex will be fixed. In every iteration, we'll fix distance of one vertex, and that vertex will be the minimum distance vertex. So so in the next iteration, one of these F, G, and H will need to be fixed, right? So F, G, and H, all three are unvisited right now, and we'll need to fix the distance of one of these. And A, B, C, D, E all have been visited. So we'll only have to look at the neighbors of F, G, and H, which are already visited. So at all points of time, we'll only look at the neighbors which are already visited. We don't look at the unvisited neighbors for the vertices. So now we look at for F, G, and H, we look at the visited neighbors. So let's say we have these F, G, and H, and we need to fix the distance for one of these. And now what we'll do is, so first let's see the vertex H here. So for H, the neighbors of H are E and D here, right? H has an H to D, H has an H to E. And both of these are visited by now because in this iteration only F, G, and H are unvisited. So only these three vertices are unvisited and these A, B, C, D, and E are visited. So H has an edge to D and H has an edge to E, and both of these are visited neighbors already. So how do we find the distance of H here, the minimum distance of H here? The distance of H will be through, if we go via this edge D, then H to D to H will be of length 4 and D itself was at a distance of 2, right? So first from A we'll need to come to D via path of length 2 and then from D to H we'll need to take a path of length 4. So in total, if we take this edge, H will need to take a path of length 6. If we come via D, H will have a distance of 6. But maybe this is not the minimum. Maybe H can be closer via the vertex E. So this H to E has a length of 1, but E itself is at a distance of 4. So what this means is uh, we'll come from A to E first with path of length 4, and then we'll go from E to H with path of length 1. So now H's distance will actually be equal to then 4 plus 1, which is 5. And 5 is nearer than the 6 length path, which we decided here. So for now, we just know that H will have a distance of 5. In this iteration, H will have a nearest distance of 5, but maybe H is not the nearest vertex. And every iteration, we find the nearest vertex, right? only one vertex distance is fixed. So here H has a distance of 5. Maybe F or G are nearer. So F and G are the other unvisited vertices yet. So maybe one out of F or G may have lesser distance than 5. So we'll need to check for F and G also. So for F, we can see the only visited neighbor of F is C here. And this edge has a length of 4. But C itself is a distance of 3 away. So what this means is from A to C path will take length 3 and then coming from C to F will take further 4. So F will be at a distance of 7 away in this iteration. While H was only something like a 5 away. So F is definitely farther than H. But maybe G is nearer. So now let's see for G now. And for G, we can see the its neighbors are B, E, and F. But F is not visited right now. Only B and E have been visited till now. So we'll see the paths via B and E. So it can be seen that hmm, if we consider the path via E, so E to G edge has a length of 6, has a length of 2, whereas E was already at a distance 4 away. So what this means is total path will be something like a 4 plus 2, which will be 6 for G. And note that 6 is again greater than 5. So we found out that the distance for H was 5, whereas we found out the distance for G is 6. So again, H is actually nearer than G also. So among H, F, and G, H is the nearest. So that's why we fix the value of H as 5 in this iteration. So yeah, so you're saying the path will be something like A, D, E, H. So yeah, that's correct, Jay, that this will be the path. And I hope you understood the reasoning behind this also. So at every iteration, we are just looking at the unvisited neighbors and at the already visited neighbors, and from those only we are trying to find out the path. So yeah, so that's how we fix out all these values. Okay, so this was the Dijkstra's algorithm from vertex A. I hope everyone understood. And now we need to answer the following statements. So if A is the first visited vertex, then the sixth visited vertex is E. So we know that A was the first visited vertex because it was just at a distance of 0. So let's see what the sixth visited vertex was. So basically in the sixth row, which was the vertex which I marked as bold. So A was the first visited, B was the second, in third row D was the third, then C was the fourth vertex, then E was the fifth, and H was actually the sixth vertex. So I hope everyone understands why I'm saying that H is actually the sixth vertex. So actually this statement will then be incorrect, that A was the first, but then H is the sixth. E is actually the fifth visited vertex because it is in fifth row. It is marked bold in the fifth row. So actually, uh, the first option is incorrect. So maybe I should we should write down for all options. So option A incorrect, as H is the sixth visited vertex. And option B says that the shortest path cost from A to H is 5. And yes, so A to H shortest path was actually 5 only. So yeah, so this statement is correct. And option C says there is exactly one path with minimum cost from A to G. So here we fix the distance of. So actually here, while doing everything, we did not encounter any case where there were multiple paths of same cost present in a vertex, right? Like for example, the minimum cost path from A to G is of length 6. And from A to G, the only path which has length 6 uh, looks something like this. the A to D, then D to E, then E to G. So this is the only path of length 6, and you can actually verify this also. And you don't need to do this manually also. If there was more than one path with minimum cost with the same minimum cost, we would have found out some tie breaking cases while doing our Dijkstra algorithm. But if you have noticed, we did not find any tiebreaker cases. Like we always had a unique minimum. So actually, there was no tie breaks. So yeah, actually, there are no two paths of same length. So similarly, the option D says more than one path with the same minimum cost is available from A to F. So A to F has a cost of 7. So this is the only path A, C, and F which has a cost of 7. And you can't find another path which will have a cost of 7 from A to F, because for it we needed some tiebreakers in our algorithm, but we did not have any ties. So yeah. So option C is correct as there is only one path, and option D is incorrect. So correct. So option B is correct that the shortest path from A to H is of length 5. And what's the shortest path? The shortest path is ADEH. Correct, as the shortest path is ADEH. Similarly, the exactly one path with minimum cost from A to G is of length 6, and the path is ADEG. The shortest path is ADEG. So here this is incorrect. The last statement that more than one path is available from A to F. So this is incorrect as the only shortest path is from A to F is of this form. So A, C, and then F. Okay. So what are the correct options? So only options B and C are correct. Hence options B and C. Okay, so I hope everyone understood this question. So this was not a very difficult question, but it was more of a revision of the Dijkstra's algorithm or how we run it manually. So I hope you guys understood. If you guys did not understand, you can ask me. I'll try to explain it again, because I believe this is one of the main takeaways of this week's lectures, the Dijkstra's algorithm, as this is very important. So everyone should understand it properly, I believe. So yeah. So then coming to the third question. So the third question says that which of the following statements is are true? So we are given two statements and we need to say which of the following statements are true or are both true or not. So the first statement says given a graph where all edges have positive weights, the shortest path produced by Dijkstra and Bellman-Ford may be different, but path weight would be the same. So would anyone like to answer in chat? Is this statement correct or incorrect? So the statement says that suppose all edges have positive weights, and suppose to find the shortest path, we once use Dijkstra's and we once use Bellman-Ford. So maybe it. So what can happen is maybe Bellman-Ford gives some other path, some path which is different from Dijkstra's, but the path weight will always be the same. Okay, so maybe I should answer this that actually this statement will be correct. And why is this correct? So just consider. So I'll just explain this via diagram. So just consider, let's say, these three vertices, which are A, B, and C. Let's name them A, B, and C. And now suppose we have an edge from A to B. Similarly, we also have an edge from B to C, and also an edge from, let's say, A to C. Maybe this edge should be a bit curved. Yeah, maybe I should. Okay, let's just assume the edge is something like this. Like this is a single edge. I'm not making it curved, but like this. So, and let's assume this edge has a weight of, has a length of 3. This edge has a weight of 1. This edge has a weight of 2. And this, maybe I should. Yeah, I'm just uh, improving the font size so that you guys can see it more clearly. Yeah. So let's suppose A to B had a edge had a weight of length 1. Similarly, B to C had a weight of length has an edge of length 2. Similarly, A to C has an edge of length 3 now. So suppose you had to find out the shortest path from A to C now, from A to C. So there can be two shortest paths, right? So A to B to C will also have a length of 3. Similarly, A to C directly will also have a length of 3. So it may be possible that when you run Bellman-Ford actually gives you this path, A to B to C. Okay, maybe Bellman-Ford gives you directly this path, which is from A to C, whereas Dijkstra's gives you actually this path, which is from A to B and then B to C, or something like this. So both algorithms may give you different paths, but since the path's length must always be minimum, so it must be unique because we have to find the path of minimum length and minimum value. So the paths may be different, but the path length will always be unique. So both these paths are minimum paths and both have length 3, even though the paths are different. So it may be possible that Bellman 4 takes one path and Dijkstra's takes other path. So yeah, so that's why this statement is actually true. That paths may be different, but path weight would be the same for the two algorithms. And from the same example, the second statement is given a weighted graph where weights of all edges are unique. There is always a unique shortest path from source to destination. So the second statement says that if the weights for all edges are unique, that no two edges have the same weight, then there is always a unique shortest path from source to destination. So actually, this statement is incorrect. And why is it incorrect? It can be actually seen from this example only. So in this example, you can actually see that all edges have different weights. One has a weight of 1, second has a weight of 2, third has a weight of 3. But but there are still two shortest paths from A to C. So there is not a unique shortest path from A to C in this. So that's why this statement 2 is incorrect. So maybe I should just type this out also, that statement A is correct as both algorithms may give different paths or may output different paths, but path lengths will be the same. And statement B is incorrect as shown in the figure. So the figure is the one which I showed you guys. So I'll attach this figure while uploading this document. So in this figure, all edges have different weights, all edges have unique weights, but there are two shortest paths from A to C. And what are the shortest paths? These are just A to C and A to B to C. A to C and also A to B to C. So yeah. So that's why only statement A is correct. So only statement is true. So I'll attach this diagram in this document later. For now, let's move on to the next question. Okay, so the next question is a bit tricky question, and I'll give you guys the answer to this, but I'll get also, uh, but I also believe you guys should think about it yourself because this is a interesting and a tricky question. So the fourth question says that consider a weighted directed acyclic graph. So note that graph has no cycles, although yeah, in which edges that leave the source vertex S may have negative weights and all other edges are non-negative. So note that this graph is special in the sense that all edges, the edges which are leaving the source vertex may have negative weights, but all other edges are always non-negative. So So it's a special case. Like it's not the case that every edge can be negative. Only those edges can be negative which are leaving the source vertex. Okay. Then the problems asks which of the following statement is are correct. Then the problem asks which of the following statements are correct. So the options are Dijkstra's algorithm correctly computes the shortest path weight from S to T. Dijkstra's algorithm may compute incorrect shortest paths. Then Bellman-Ford correctly computes shortest path, and Bellman-Ford may compute an incorrect shortest path. So these are the four options. And this is sort of an interesting question. So I want you guys to think about it a little because, yeah, this is a bit non-trivial and offers some insights into these algorithms. So first of all, so maybe this problem is just asking us that for Dijkstra, does it give a shortest path or does it not give a shortest path? And similarly, option C and D ask us to distinguish between whether Bellman-Ford gives the shortest path or it does not. So let's just ask with the let's just start with the simpler one. So out of option C and D, what do you think is correct? Like, will Bellman-Ford compute the shortest path or will Bellman-Ford may fail to compute the shortest path in this problem? So I'm giving you guys 2 3 minutes to think out and maybe just type out in chat if you feel like. Okay. So Rasika is saying that out of C and D, option C is correct. That Bellman-Ford correctly computes the shortest path. So yes, Rasika, you're correct. That option C is correct. And why is this correct? As Bellman-Ford always computes the shortest path, even in negative weights. As Bellman-Ford computes the correct shortest path, even in negative edges. Even if graph has negative edges. Even if graph has negative weight edge. Okay. So option C is correct. So option out of option C and D, only option C is correct. Now comes options A and B. So out of options A and B, which of the following is correct? Will Dijkstra compute the shortest path or will Dijkstra not compute the shortest path correctly? Again, I want you guys to think about it. Maybe If you guys have any intuition or anything to say, you can type it up in chat. Okay. So Rasika is saying option B, that Dijkstra may compute an incorrect shortest path. So I believe, Rasika, your reasoning may be along the lines of saying that Dijkstra fails in case of negative weights, right? So it is in general true that Dijkstra fails in case of negative weights. But the problem here, the negative weights have a special structure here, that the vertices that only negative weights can only be for the edges which are leaving the source vertex. And for all other edges, weights are actually non-negative. So do you still think that uh, Dijkstra will compute incorrectly, or will it give correct? So Rasika has written chat yes. So what do you mean by yes? So will this still be incorrect, or will this be correct? Yeah. So Rasika is saying not sure. So yeah, I think that's a good response. Like, because it is better to be not sure than be incorrect. Yeah. So actually, so maybe we can just look at something. So maybe I should give you guys an example. So not exactly an example, but let's just see an example where Dijkstra actually fails, even in case of negative weights. So when may Dijkstra fail? So Dijkstra may fail when, suppose this is source vertex, let's say this is A, this is vertex B, and suppose this S through A had a weight of, let's say, -1. So we are assuming that we have negative weights. And now let's say there was another edge of from S to B, which had a weight of -10. But now let's assume that A to B had a weight of -20. So in this case, actually, uh, Dijkstra fails. And why is this the case? So let's say we start from the source S. So when we start from the source S, we'll need to look at the nearest neighbor. So out of A and B, B is nearer to S, as B is at a distance of -10. And -10 is lesser than -1. So that's why the Dijkstra algorithm will fix the distance of B as -10 from S. So B will be at a distance of -10 from S. And after that, Dijkstra will fix the distance of A as -1 from S in the second iteration. But note that actually B may have a much smaller distance than -10. So it would have, so what we could have done was, maybe if we took this path, which is S to A to B, this path has a length of -21, which is smaller than -10. So actually shortest path from S to B is of length -21, whereas Dijkstra's gave us the answer as -10. So this is the example. I hope everyone understands the example where Dijkstra fails. So this kind of example would have been covered in the lectures also, but just remind you guys about it. So this is the kind of example in which Dijkstra fails. But note that here in this example, uh, uh, so at least for the example which I'm discussing, this property does not hold. So so the property was that S, or the only negative weights may only be for the edges which leave the source vertex, and all other weights should be non-negative. But note that in this example, uh, this -20 weight is for an edge which does not leave the source vertex. So actually, this example does not uh, apply to apply to this question. But note that it may be possible that some other example, we may come up with some other example where Dijkstra fails. But actually, it's a very interesting property of Dijkstra that it only in this type of graphs where the edges which leave the source vertex have negative weights and all other edges are non-negative, in these sorts of uh, graphs, Dijkstra actually works. It does not fail. So it correctly computes the shortest path. So so suppose instead of this -20, this edge was of length, let's say +20, or it was something non-negative, like instead of -20, it was 0 or +1, +2, or anything positive. Then this example would actually, then in this example, Dijkstra will always work because I have not given you any reason why this works, but this is, let's just assume, a property of Dijkstra for now, that Dijkstra always works if the negative weights are only for edges which are leaving the source vertexes, and all other edges have non-negative weights. In that case, Dijkstra actually always works. So yeah. So maybe discussing the reason for this. So the high level intuition of why Dijkstra works, even if if just the edges leaving the source vertex have negative weights, but all other edges have positive weights. So the intuitive idea behind this is very similar to Dijkstra's algorithm only. So what actually happens is here, if some other, so if A to B edges, so I'm not going to give you guys a proof for why Dijkstra algorithm works here, but just give you guys an intuition of why is it working. If this was not -20, and if it was just, let's say, uh, let's say instead of this -20, it was, I don't know what's happening right now. So, instead of this -20, if this was +20, or let's say anything positive, then Dijkstra would have always worked here. And the high level idea is, so in the initial step, so why does this case fail? Let's see why this case fails actually. So the high level idea of why this case fails is, the source initially greedily picks the smallest distance to the vertex. So from the source, it picks the nearest vertex to it. And the nearest vertex out of A and B is actually B, because it is at a smaller distance, which is of -10. But what may actually happen is, there might exist another path to B through some other vertex other than the source. So, so B may contain another edge, let's say this -20 edge, which was actually from a vertex which was not from the source, which was, let's say, this vertex A here. Or there may be some other vertex C, D, E, which has a large negative weight, but that edge is not connected to the source. And because of that large negative weight, uh, it may be preferable for B to take this path instead of this -10 path. So this -20 path has a smaller weight, so it may be preferable for B to take this path, this B to A to S path, instead of directly this B to S path. But note that this is because of a very large negative weight being present, such that such that the other endpoint of this edge is not S. If the other endpoint was already S, then S would have picked this edge, right? So suppose this -20 edge was also connected to S only, then the initial step, uh, S would have picked this edge itself. But right now, since this -20 is not visible to S, so S only looks at its neighbors, and now it can only see this -10. So that's why S fixes the distance of B to -10. But if B had some other edge like this, then this -10 would have been incorrect. But suppose B did not have any edge like this, B had a distance of 20 or something like this, then we can pretty much easily be sure that this kind of situation won't arise, that there will be no other in neighbor of B which will have a negative weight. And so the B distance will actually be calculated correctly. So I hope you guys understand the intuition behind what I'm trying to say. So this intuition can also be formalized to give a proof for this, that Dijkstra will compute the shortest path in this case. But I don't want to get into that, and uh, I just want to give you guys an intuition about this for now. So I hope you guys understand why is this the case. If you're not sure why is this the case, then you can maybe let me know via chat and I'll try to explain the intuition again. Otherwise, I'll just assume that you guys have a high level idea of why Dijkstra works here. So actually, option A is correct. So even though Dijkstra fails in case of negative weight edges, uh, surprisingly, or maybe not surprisingly, just like this, it works if the negative weight edges if only the edges leaving the source can have negative weights. Something like this. So Dijkstra fails in case of negative weight edges in generally, but it works if only the edges leaving the source have negative weights. That is a very interesting property. Like one may guess at the first try that, oh, we have negative weights, so Dijkstra will not work. But actually, if just the edges which leave source are negative and all other are non-negative, then Dijkstra actually works. This is a bit, that's why this was a bit interesting question for me because, yeah, this is something which is not quite trivial. And options A and C are correct. So you can use Bellman-Ford as well as Dijkstra here. And since Dijkstra is faster, you will prefer to use Dijkstra instead of Bellman-Ford. So now we'll come to the fifth question then. So fifth question says, how can we use Floyd-Washer algorithm for all pair shortest paths to detect whether a graph has a negative cycle? Consider that SP is the resultant matrix of Floyd-Washer algorithm. So this is the problem. So maybe you guys can think about this problem for let's say 2-3 minutes. Meanwhile, I'll just go and get some water for myself. So think about this, and if you think that your answer is correct, maybe you can type in chat what you think is the correct answer. I'll come back in 2-3 minutes, guys. Okay, so sorry guys. So no one has written anything in chat. So actually, so Freud Warshall is actually used for detecting a negative cycle, and the problem asks us how do we actually detect for negative cycle. So so if we want to find out a negative cycle, so uh, a cycle starts from the same vertex and ends at the same vertex, right? So that's the property of a cycle. So we just and an entry of sp of an entry in the shortest path matrix from, let's say, I to I, from a vertex I to that same vertex I, will give us a path which starts at I and ends at I. And if there is a negative weight cycle, this path will have a length less than 0, right? Because we have found out a path of length less than 0, which is actually the negative weight cycle. So actually this option B is correct, and you can see about in lecture videos also. And yeah, it's a very straightforward statement that to check whether a graph is a negative cycle, we just check whether SPI comma I is negative after we have run the Floyd-Warshall algorithm. So yeah, because from I to because Floyd-Warshall algorithm finds the shortest path from a vertex I to the vertex J, so it will find the shortest path from I to I itself. And if we are talking about I to I path, then it's just a cycle only, right? And if the cycle has a negative length, then this entry will be negative. So yeah, so answer is option B. So I hope everyone understands this. If it is not clear, let me know via chat. Okay, so Rasika is saying that Floyd-Warshall cannot be used to detect negative cycle. Actually, Rasika, Floyd-Warshall actually can be used to detect. As I just mentioned that you just check if SP of I comma I is negative. If so, then you have found out a negative cycle. And option B is correct, as SP of I comma I denotes the shortest path from I to I using all possible vertices. And if this path or maybe yeah, using from I to I with at most n edges. Maybe this is a better. So SP of I comma I denotes the shortest path from I to I with at most n edges. And if this path has negative length, then this means that I is part of a that vertex I is part of a negative weight cycle. So I hope this is clear to you, Rasika, that why Floyd Warshall can actually be used to detect negative cycles. So okay, you got it. Nice. So then maybe we can move on to the sixth question. Okay, so maybe we should not be discussing the sixth and seventh question because I don't think it's too tricky, but it will just take a bit more time since yeah, maybe I should just remove the sixth and seventh questions because these are more of time consuming questions rather than questions which are very interesting. And I believe I'll also be closing the session a bit earlier today because I'm feeling a bit unwell today. So sorry for that, guys. But yeah, maybe we can continue right now. So let's come to sixth question then. So the new sixth question. So this question is from the ungraded assignment. So in the ungraded assignments, yeah. So yeah, this is from ungraded assignment. So the problem asks us, suppose you have a simple undirected edge-weighted graph and you have to compute the shortest path between a pair of vertices u and v. After which of the following changes to the edge weight described below will the shortest path not change? So suppose you have a simple undirected graph and we want to find the shortest path between a pair of vertices u and v. And so, and we want to find out which of the following operation actually, after which of the following operation the shortest path will not change. Note that the weight of the shortest path may change, but the problem is asking is that the exact shortest path should not change. So after which of the following changes will the shortest path not change? Its weight can change, but the shortest path should not. So what do you guys think? Maybe we can take this option by option. So do you guys think that if all edge weights are increased by one, the shortest path will remain the same, or maybe it can change? Would anyone like to answer this in chat? Let's think about what do you think. Like, no need to give a proof or anything. Just what do you feel? Like, if I increase all edge weights by one, will the shortest path change or will it remain the same? So actually, the answer to this is so since no one's typing, I'll just help myself. So option A, here the shortest path can actually change. Shortest path may change. And why is this the case? Just consider an example. So let me draw an example for you guys. So consider this vertex as vertex A. This, okay, so let's just consider these vertices as A, B, C, and D. And let's assume all of these have edges between them. So A to B, similarly B to C, and similarly C to D. So yeah. And let's suppose all these edges have weight 1. And we also have an edge between A to C directly, A to D directly. And this edge is something like this. So yeah. And this edge has a weight of 4, let's say. So I hope the font is clear to everyone. Otherwise, I'll just zoom in. Yeah. So this edge has a weight of 4. This A to D edge has a weight of 4, whereas these three edges have weight of 1. So now what happens if so now right now it is easy to see that the shortest path between A to D is of length 3, which just takes this route, A to B, then B to C, then C to D. But what happens if I uh, increase all edge lengths by 1? If I increase all edge lengths by 1, this edge becomes of length 2. Similarly, this edge becomes of length 2, this becomes of length 2, and this becomes of length 5. Now it can actually be seen that this ABCD path now has a length of 6, whereas this A to D path only has a length of 5. So now this A to D becomes the shortest path instead of the initially the shortest path was this ABCD and this A to D path was longer, but now if we increase all edge weights by 1, this A to D becomes shorter than this ABCD path. So Rasika was saying that the shortest path remains the same. I hope you get that in this example, the shortest path actually does not remain the same if we increase all edge weights by 1. So the intuition behind this is shortest paths. So different paths may contain different number of edges in them, right? One path may contain 5 edges, one path may contain 10 edges. Like here, this ABCD path had 3 edges, whereas A to D path only had 1 edge. So now what happens is if we increase all edge weights by 1, uh, the path having 3 edges will have its weight increased by 3, whereas the path having only 1 edge will have its weight increased only by 1. So that's why A to D now can become smaller than ABCD path, because ABCD path will increase by 3, whereas this path will only increase by 1, as can be seen here. That's why this holds. So this option does not preserve. So, and so I'll attach these diagrams later, as I've already said. So right now, I'll just mention about these diagrams that this is the figure discussed. Okay, and maybe I should just write down. In the given figure, A, B, C, D is the shortest path initially, but AD becomes the shortest path later. So yeah. Now option B is all edge weights are multiplied by 2. So if all edge weights are multiplied by 2, will shortest path change or not? So would anyone like to guess? I believe this is a straightforward question. One. So Rasika, do you think if all edge weights are multiplied by 2, the shortest path? So yeah. So Rasika is saying that the shortest path will not change. So yeah, actually that is correct. And good job, Rasika. So shortest path remains the same. And why is this the case? Because if we multiply by 2, let's say we multiply every weight by 2, so all paths, the weight of all paths will be multiplied by 2, right? So if something was minimum earlier, like if 3 was less than 5, then 6 will be less than 10 also. So that's why the shortest paths remain the same, as all paths will have length multiplied by 2. Weights multiplied by 2. So yeah. And so their minimum remains the same. Similarly, in option C, if all wedge edge weights are half, then again, by similar argument, we can say that shortest path remains the same. I'll just copy and paste this argument, as all paths will have weights half. And so their minimum remains the same. Similarly, option D. Now option D is all edge weights are decreased by 1. So if all edge weights are decreased by 1, will the shortest path change or will they remain the same? So I believe you can answer this by the discussions we have already had earlier, that uh, in this case also the shortest path may change. And why is the case? Just consider this example again and just consider this as the initial graph, the bottom graph as the initial graph. So here initially this A to D was the shortest path, but if all edge weights are decreased by 1, then in this graph, ABCD becomes the shortest path. So yeah. So here shortest path may change. Shortest path may change. Similar reasoning to option A. So I hope everyone understands. So option A and D shortest path may change, and in option B and C it will remain the same. So option B and C is the correct. So hence options B and C are correct. So I hope everyone understands this, and if you don't understand, you can ask me in chat and I'll try to explain it better. So in option A and D, the shortest path may change, whereas in option B and C, it will not change. So yeah. Okay, so I believe this problem 7 is all 7 and 8 are also from your ungraded assignments, but maybe these are not uh, so difficult problems. Like these can be done by you guys yourselves. Like I wanted to discuss this of problem 6 because in this uh, you guys should be able to come up with examples where the edge weights actually like where the shortest path may change in options A and D. That's why I discussed this problem. But I believe in this problem 7 and 8, this Spider-Man one, you can check it out in the ungraded assignment. This problem is there. It's not too difficult to answer yourself. So maybe uh, I can leave out these problems for today also. So I'm sorry guys, but it's just that I'm feeling a bit unwell today. So uh, I don't, I want to avoid discussing too many problems. So yeah. So maybe we should not discuss problem 7 also. So yeah, I guess these were the main problems which I wanted to discuss for today. So so yeah, there were some other problems also, but yeah, I believe they are not really necessary to discuss right now. So I guess we have discussed all the problems for today, guys. So if you have any questions or comments or anything you may want to say, you can let me know via chat. If you have some other problem which you want me to discuss, maybe you can ask me that also, since we have some time, like we have some 20 minutes or something. And like, if you don't have any uh, problems to discuss or anything, then maybe we can close the session for today a bit earlier. So if anyone has any doubts or any comments or anything, feel free to write in, type in chat. Okay. So Jay is saying that there are no doubts from his side. So I believe since no one is asking any doubts in the chat, then I believe like everything is clear to everyone from today's session. So everything is clear to everyone. So yeah, so I hope so I guess we can close the session for today. And so yeah, once again, thanks for joining, guys, and hopefully we'll see you guys next week also, same timing, 6 to 8 p.m. So yeah, thanks for joining, guys, and I'll just stop sharing and you may leave now. Thank you and bye bye.